consider the situation for me real quick on the computer screen. All right, we got a guy up in the first scenario with a horse pulling on either side, and he holds a smile. Okay. The second situation, this guy is holding onto a rope onto a tree and being pulled by a horse, and he's still holding the same smile. Okay, and so the scenario here is showing that those two things are actually equal on the guy as far as how hard it feels. But all of a sudden, you take those two horses that were pulling on both sides up top, and now they're pulling on the same side, and now there's a different situation. He's got a frown, he's miserable, and so there's got to be something taking place here in which two horses, depending on their placement, do something different to the guy in the middle, okay? And so when we talk about Newton's third law of motion, we're going to pull this idea into that, all right? And so I'm going to go ahead and use a Prezi, okay? And I got to back out a little bit. There we go. We're going to use a Prezi real quick here and just kind of go through the notes of Newton's third law of motion and then show just a short video, okay? We call this the action-reaction law. All right, so for every action, we've heard this a million times, there's an equal and opposite reaction. The force on one thing hitting another, the other thing experiences the same force. That can be a baseball hitting a bat, that can be a rocket taking off and traveling through space or through the air that it's trying to get through. It could be me pushing an object, okay? If I push a door open, that door is pushing back on me. Makes sense, right? Okay? No matter the size, you can only push or pull as hard as something can push or pull you. And so look at this guy pulling the wall. He's pulling as hard as he can, and we've got a number on the scale of 500. All right? Now, why is that number not going way up when the wrestler is pulling? Even if the wrestler is winning the tug-of-war match, it's still only 500. It's only as high as the weakling can push, okay? And I can show that by punching a piece of paper. Doesn't hurt my hand at all, does it? Because the force interaction is only as much as it can push back on me, okay? But I do that same thing on the wall, and now there's some pain involved because now we've got something here that's definitely providing more force back on me, and so I feel it, all right? Kind of a weird concept, but go ahead and sketch this out for me, take down the notes, and we'll move on, okay? So pause it. All right, watch this video for me on physics on football. It might be a little quiet. I'll pause it along the way.
One of the things we study in physics is the interaction between objects. Check out this interaction between these objects. Great job, guys. Now, who felt the greater force in that interaction?
Well, I guess I did.
Well, actually, it's one of Newton's third law of motion that states for every action there's an equal and opposite reaction. You both.
Okay. The little guy said, I felt the most force. But when the two butted heads, the law says that they experienced the same force. But we definitely saw a difference. They just didn't cancel each other out and sit there, did they? Okay? We definitely had some movement taking place, okay? And what he's going to explain is that there's more forces involved than just butting the two heads together, okay? When we look at a system amongst what's taking place, the two heads butt, but also there's other interactions that take place, for instance, feet versus the ground, and all of a sudden now we may get some movement in one or other directions, okay? So watch the rest of this.
Oh, the same thing. Let's demonstrate with the scale. Now, it's safe to say you're stronger than me, right?
Yep.
All right. It doesn't matter how hard you pull on your scale, my scale reads the same number. What's true for pulling is true for pushing. You and Corey felt the same force.
Well, how was I able to blow off line?
Well, there are other force pairs involved, namely between you and the ground. You push against the ground and the ground pushes you forward. If you push the ground harder than the other guy, you lose him back.
Cool. So I guess it was like hotel keep our feet in there.
Exactly.
I All right, let's demonstrate that.
Whoa, wait a minute.
All right? So kind of a simple concept, okay? Whether or not you've got a hammer hitting a nail, whatever, we call these interactions that take place, we call them mutual interactions, okay? And, sorry, my phone's going off. These mutual interactions take place all the time amongst two things. Those two things interacting with each other in some way. Again, golf ball, golf club, there's an interaction there, and with those interactions we have forces, pushes or pulls, and those pushes or pulls are going to equal each other, okay, within that system. Take that down. All right. The question here that I have is, how far can this go? I hit a golf ball hits my golf club. Golf club exerts a force on ball exerts force on golf club. Can that take place? I mean, is that the same situation with everything? What about a bug hitting a windshield? Yeah, there's an interaction there, but are the forces really the same? If the forces were the same, to me, I think bug goes splat, comes to a dead stop. Car should go splat, come to a dead stop. But that's not the case. And one thing that we have to pay attention to is that second law equation, acceleration, force, and mass. Because with acceleration, force, and mass, something more massive accelerates less, okay, or decelerates. So when it comes to this car and this bug, a real small object with little mass like a bug accelerates or decelerates a lot. Same with the golf ball, off it goes. Or the bug, down to a dead stop. But the big object, the club or the bat or the car, it hits whatever it hits, and it's got very little acceleration or deceleration because it's so massive. And so you have to remember acceleration and force are directly related, and acceleration and mass are inversely related. All right, same thing with the cannon and the cannonball. The cannon's massive, okay? It's got a lot of mass. It's got some force on it, okay? Let's just plug in some fake numbers. Watch this. Ready? Assume that on the F is a 1, a force of 1, whatever that is, okay? And the mass is 100. Well, 1 over 100 is 0.01. What if all of a sudden the same force was on a small object? So now we have a 1 because the forces are equal, and the mass of the ball is just 1. It's 100 times less. 1 over 1 is an acceleration of 1. That's a lot bigger than 0.01. So off the cannonball goes accelerating because it had a tiny mass, and the cannon just kind of sits there because it was massive and had very little acceleration at all. There's some acceleration, kicks back, right? Same thing with a gun. The bullet goes off flying because it's tiny, and the gun kicks back in the opposite direction. Forces are equal, but their accelerations are different because their masses are different. All right? Simple concept. We're almost done. We can also look at helicopters, birds, and rockets, and they're all pushing on something to take off. They have to. Otherwise, they just sit there. There's an interaction that takes place. What is a helicopter pushing against to sit up there in the middle of the air? All right? If it's just up there hovering, what's it pushing on? It's pushing air down. And so are rockets. They push air down and they go in the opposite direction. We call that lift. Okay? And we see that with planes and everything. Okay? I think that's the end. Yes, it is. All right? Back to our scenario here. Why is this guy in pain? Because he's got a force over here on the tree, and he's got 2 horses pulling in this direction, and that's twice. I mean, you've taken, if each horse can pull, was just make a fake number of 100, well, 100 this way and 100 this way, and he's fine because he's only getting pulled by the force of 1 horse, okay? The weaker of the 2 horses. But when they're both on one side, now he's got like 200 going this way. And so he's struggling to handle that, okay? And hence the frown. All right, so this is Newton's third law. You have one assignment. Now that you've watched it, I hope you watched it all the way to the end. I am going to open a blog comment, okay? I want you to give me 2 examples of an interaction in which the forces are equal, okay? An interaction in which the forces are equal. I talked about a number of them in the presentation. Don't use anything that we've mentioned. Think of something fresh. Just an interaction of 2 things in which, when those 2 interact, the forces on them are equal. Okay? 2 examples on my blog. Okay? Don't forget to put your name on it. That's it for now. We'll see ya.